So I'm going to give you a talk. I don't really know how long it will take, but if you want to stop me, just stop me if I'm running over. And what I'm going to do is I'm going to talk a little bit about careers in healthcare technology and how to get to a point where you might be having a career in healthcare technology, and why you might want to do that. Why would you want to take all the things you've learned in your undergraduate studies and then maybe apply it to this domain? And then I'm going to tell you a little bit about my own journey. How did I end up here? Because I didn't start off doing an engineering degree. I started off doing a completely different degree. So how did I end up coming into healthcare technology? And one of the most important things, I think, for me in my job here at King's is I was working with people. And really, this means like colleagues and students. And these are just some photos to show some of the times in the past that I do that. So this is one of my former PhD students, Wang. And this is Caroline and Jackie, and they are sonographers. They do ultrasound at St. Thomas's Hospital, and we were working on a robot to do ultrasound scanning there. And these are some of my undergrad students from summer school. So I teach over the summer in King's Summer School, and we're just in the X-ray room, posing for a picture there. So. Technology, what is it? Well, here's the definition from somewhere online. So technology, to create something via techniques, skills, methods, and processes to accomplish a specific objective. So basically, you've got something to do and you're going to use your knowledge and your skills and techniques and everything you've learned to actually go and accomplish it. And that process is then called that thing is called doing all of that is called technology. So technology is nothing new. So one of the subjects I teach is human anatomy and physiology. And here's the sort of evolutionary timeline to get to Homo sapiens, which is us. And actually, you can look at some technology that came very early. So about 3.5 million years ago, we started to or our ancestors, evolutionary ancestors, started to use stone tools, so Australopithecus. So tools and the use of tools is an example of tech. And then we control fire, and then we started to cook, and then we started to have clothing. And I had this slide in a different lecture, and I put it in this one. I was thinking, obviously, these are examples of tech, and in fact, we could relate them to modern types of technology. So tools of mechanical engineering, fire, chemical engineering, clothes, materials, science, dwelling, civil engineering. But of course, what we're talking about right now is modern tech. So modern tech is quite diverse. And I just listed a few examples. So communication technology, entertainment technology. Of course, the PS5 was just released a few days ago. Still haven't got one, but can't wait to get one. Technology for energy production and storage and so forth, transport technology, and of course health care or health technology, a really important type of technology because it's so impactful on our lives and because our health is very important to us, and therefore healthcare technology is going to be an important subject area for society. Now, humans are very unusual, and in that if we look at a human being, a human expends about 100 watts of energy, or that's the power of the human. So 100 joules a second, and that's the energy that we basically need to be in homeostasis. In other words, just to maintain a steady state. So this is typically the energy expenditure at rest for a human. So each of us is like a 100-watt light bulb. But actually, if you look at human energy consumption, it's absolutely huge. And these are some graphs showing the population of the Earth up to the start of the millennium, and the energy use from primary energy sources. And actually, I just got an updated figure for 2019. So we last year we used approximately 600 exajoules. And actually, if you go back to the previous slide and you think, okay, 100 watts and roughly 7 billion people on the planet, how much energy is that? And compute it per annum, it actually only works out to be 22 exajoules. So human beings on the planet only need 22 exajoules just to survive, but actually they're using 600 exajoules, which is about 30 times what they need. And actually, if you look at all other living things on the earth, no one does this. They only use what they need to be homeostatic. We are the only living things that actually go above that. And actually, right now, we're using 30 times more energy than we require for homeostasis. So that's just totally incredible. And then actually, if you go and look at energy consumption, we can use energy consumption to really be a marker of the level of technology that a civilization has reached. And this is what Kardashev proposed. And he made this scale to say that actually, if we use a certain amount of energy, then we have reached a certain level of tech development, or level of technology. So in his proposal, there were a number of types of civilization. So type 1 civilization is a civilization that uses as much energy as falls on its planet. So if we could harness all the energy that fell on the surface of the Earth, we would be a type 1 civilization. A type 2 civilization uses as much energy as is produced by its star in its solar system, and a type 3 civilization uses as much energy as is produced by all the stars in its galaxy. So this is it's a logarithmic scale which is used to describe this evolution from the various types. And actually, we are currently 0.73 on that scale, and we are anticipated to reach type 1 in about 100 to 200 years. So in about 100 to 200 years, our annual or our energy expenditure will be equal to the energy falling on the surface of the Earth from the sun, which is amazing. So we're not that far away. Now, why is this relevant to my talk? The reason is that actually the technology is linked to societal development and well-being. And that's a key thing that's tied together. It seems like the better technology you have, of course, the more energy you consume, and it should follow that societal well-being improves. And actually, this is really important for healthcare technology, because you can directly understand how like a healthcare technology would have an impact on societal well-being. But just generally, technology itself has generally has a positive impact on societal well-being. And that's a really good thing to try to link and look at some of the understanding behind that. Now, why focus on healthcare technology? Because, okay, so technology has a positive impact on societal well-being, so you could look at mostly any technology and work in that domain. But why healthcare technology? Well, there's some major problems facing humanity at the moment, and literally the amount of disease that's present is a problem. And the burden of disease, just amount of disease, or the proportion of disease in the population, is increasing. And there are a number of reasons for that. And some of the main reasons is that the population is aging. People are just living longer, and people who are older just tend to have more illnesses, because the human body is an organism, and organisms deteriorate with age. And there's other huge areas that need attention. So there's cardiovascular disease, cancer, diabetes, and of course we just know right now, because we're living through a pandemic, there's infectious disease as well. So all of these things are like, they're not declining over time. They're actually getting worse over time. And another huge problem is like only a small fraction, so about half, not a small fraction, but half the population of the earth have access to the basic healthcare provision. The other half don't. So these are huge problems, and we don't have any more money or any more trained healthcare professionals to deal with these. So we need to come up with other solutions. And really, the solution is to try to make the healthcare provision more efficient, and also to make it more accessible. I should add plus accessible here as well, because half the people on the planet don't have access to healthcare. And technology is one of the key ways in which we're going to do this, because with technology doesn't mean that we're going to pump in more money, and technology doesn't mean that we're going to require more staffing. It actually is the opposite. It can provide solutions without the demand for extra finance and staffing. And therefore, because of this, like what's going on right now, and the fact that technology is going to be very impactful for our future of healthcare provision, it's a good one to consider for a career, and the careers are booming in this area. And of course, as I've already explained to you, it's going to have a lot of societal impact. So if you get involved in this area, you can do a lot of good for society. And I think these are good reasons why to consider a career in healthcare technology. So for humans, hopefully we stay healthy, but if we get unwell, so we get a disease, we then become a patient. And what happens to a patient? A patient goes through a patient care pathway. So first of all, we need to find out what's wrong with the patient. There's a diagnosis. We need to choose a suitable treatment, because often we can have many treatment options for a patient. And then we need to plan that treatment. We need to actually guide the treatment. And then we need to monitor the patient as well afterwards to see how they're getting on, either when the treatment is finished or when the treatment is ongoing. So these are all like different parts of a patient care pathway. And technology has a role in all of these parts. So even being healthy, technology has a role, because we talk about the worried well. So these are people who they don't have a disease, but they just want to use technology to help them to stay healthy. So for example, if you have a weighing scale or a blood pressure monitor or a heart rate monitor, or you're monitoring your glucose levels as well, just to make sure that you don't get some early signs of diabetes and so forth. That's just tech for worried well. That's a big area right now. And also for people who people who are working out and so forth, they want monitoring systems and so forth. And so this is a big area of healthcare technology, but it's not aimed at people who are sick, but it's there to keep them well. And of course, we want to deploy technology for prevention of disease. That's like the holy grail, to stop a disease from happening. And that's really like the very hard thing to do, but it's again an important area. And then we've got tech deployed in all different stages of the patient care pathway. So we're going to be deploying tech in all these different areas. Okay, next. So, how do we get into a career in healthcare technology? Well, I'm sorry, one of my colleagues is trying to reach me on Teams, so getting annoying pop-ups. I apologize for that. How do we get into a career in the area of healthcare technology? Well, there are lots of options, but I'm going to just highlight a couple of areas that may be important. So you're right here doing your undergraduate degree, and you could go from being an undergraduate student and you could go to a medtech company. So there's so many medtech companies. There's lots of huge medtech companies. In fact, the medtech companies, some of the biggest companies in the world. So companies like Johnson and Johnson, Medtronic, all the imaging companies, Philips, GE, Toshiba, Siemens, and so forth, huge international companies that sometimes they don't just do medtech, they do lots of other types of technology as well. For example, most of the railways in the country, all the tech in railways is made by Siemens. Then you've got smaller companies, so small to medium companies, which are very rife in the UK, where we're really a international hub for small scale medtech, and of course then startups, like companies that literally are just a couple of people with an idea that's just got going. So you could go into these companies, and actually what's interesting is a lot of especially the larger companies have graduate training schemes where they'll take graduates and they'll put them through their training scheme with the goal to get to some target level within their company. The larger companies also will sponsor you to go and do some more studying, so do a master's course, or go into a research program like a PhD program as well. So this seems very attractive to go down this route. So get into a company and maybe they even sponsor you to study. And there's lots of opportunities in medtech or healthcare technology. That's actually a very big area, certainly in the UK, Europe, and just internationally, it's just a big area. Other things you could do is you could go and do a research degree at a university and then stay at the university doing research in healthcare technology. And that's another career option. And often we work with companies at universities, or of course you could go into the National Health Service or another health service and go in as a clinical scientist. So clinical scientists in the NHS, for example, will look after all the healthcare tech in hospitals. So they do maintenance, they do quality assurance. They have they look after labs that do careful measurements for healthcare professionals on patients and so forth. There's a range of activities that clinical scientists do. And for example, at King's, we're one of the leading centers for training of clinical scientists in the UK. So we train both clinical engineers and medical physicists. And if you join, you get to do a master's. So you work for the NHS, you get to do a master's program part-time over 3 years. And then at the end, you become a qualified clinical scientist. It's quite a lucrative position as well. So these are some options of how you could access this this career. Basically, there's a number of different options, and each has its pros and cons. Now, what about myself? What did I do? Well, I started off studying medicine at Guy's and St Thomas's, which is now part of King's, and then after that, I left for a little while to work in a company doing mechatronics engineering, and in fact industrial imaging, mechatronics engineering. And then I started my PhD and became an academic at university. And I've actually worked my whole career has been based at King's. Actually, I started working in 2001, and so it's 20 years celebration in January. And that's the route I chose, but you know, it could have been different. But what's nice is that if you see this little purple arrow, that all these three different things work nicely together in projects. So me being in a university, I still work very closely with the NHS, because actually I'm based at St Thomas's Hospital, and many of my colleagues are doctors working for Guy's and St Thomas's or King's College Hospital. And I also get to work with companies because a lot of my projects involve companies, large scale and SMEs. So even though I'm here, I still get to work across with the other two bits of my diagram here. So what do I do? Well, in a nutshell, I try to do things which are innovative and are going to be impactful and are going to make a difference to the well-being of patients or healthcare professionals or other parts of society. And so I don't do any one single thing. I just tend to look at projects that are meaningful and then engage in those projects. So some of the things I have done and am doing are listed on this slide. So making measurements from medical images was probably where I started off in my research career. So just accurately measuring or robustly measuring things from medical images, obviously to inform some clinical decision making. Using medical images to help to guide keyhole or open surgery in patients. And then moving on to robots. So we've recently been working on ultrasound robotics, making robotic devices that go inside patients for keyhole surgery, robotic catheters, and actually looking at robotic systems that are actually very autonomous. So having very little user input and trying to do complex things by themselves, autonomous systems. And then actually probably my most recent stuff is on additive manufacturing, so 3D printing, building models of human beings that can be used for simulation and training, and actually even building implants for patients, and building new types of 3D printers that can basically do printing that would be useful for healthcare applications, but actually to do it really economically, do it really cheap, so it's very accessible. So these are some of the areas I work on. I'm just going to whiz through this stuff just to give you an idea, because if you want to know more details about this stuff, you can come and talk to me. You're welcome to do that. So this is just some examples of like measuring stuff accurately. So one of the procedures that I know a lot about, because I worked in this area, is the treatment of cardiac arrhythmias. So heart beating not in its normal pattern. And one of the most common arrhythmias is something called left atrial fibrillation. And a lot of the times it arises in the left atrium of the heart. And so when you need to treat it, you can treat it with keyhole surgery, but you need to know the shape of the left atrium really well. So this is just an example. So this is an example of using a CT or MR images and actually then extracting out the left atrial shape. And this is all of these pictures are atria from different patients, and the algorithm we developed to extract out the shape accurately. And of course, that's then used to help the clinicians do their decision making and do the procedures that they are going to do to treat these patients. And then next, as an example, it's actually once you got the shape of the atrium, you can then use it to help the doctors to treat the patient. So this is these little blue models are the models of the left atrium that we extracted from the previous work. Now what we can do is like align them to the X-ray images of patients who are undergoing the keyhole procedure. So these things that you see moving around here are devices inside this patient's heart, inside the left atrium. And we've superimposed the left atrial data on top of the fluoroscopy images so that the doctors can actually see where the left atrium is, because otherwise they wouldn't be able to see this because it doesn't show up in X-rays. And thereby, this is known as a image-guided system for doing surgery. And this work was actually done in partnership with Philips. So Philips is a huge company. They make all sorts of things from shavers, light bulbs, and of course they make imaging systems. And we worked with Philips, and we developed this actually all the way into a product. And this is sold with their X-ray system as an add-on piece of technology So when you buy their X-ray lab, you can request this product, which is called EP Navigator, and it was released in 2008, and yeah, it's still available as a. You can go onto Philips website, Google the EP Navigator, and you'll see it there listed on their, be described on their website. And we worked, of course, with guys in St. Thomas's hospitals to actually test it out when we were developing it. And once, of course, we did all that, then Philips then took it all the way to commercialization. So this is a nice example of something that we made and it got commercialized. And it's literally can be found in hundreds of places. When you go to hospitals, you'll find this package. And sometimes I've visited and found myself walking into a cath lab where they're using the stuff that me and my team built. In each of my slides, I've put a picture of my team members who actually did the work, or did most of the work. This is another example of a similar thing, but this time different in that we're not using information extracted out of like shape of a chamber of a heart or something extracted out of a CT or MR scan. But this time what we're doing is we're taking ultrasound information, and that's what you see in the color here, and we're combining it with X-ray information. And so this thing here is an ultrasound probe, which is inside the body of this patient, and this patient is having their aortic valve replaced via a keyhole procedure. And normally when you do this procedure, you need to use two types of imaging. You need to use X-ray imaging, which is the gray stuff here, and you need to use the ultrasound image. And they're actually on separate screens, and they're not aligned. And what we did was develop a technology to track the position of this ultrasound probe, and that's what you see here. This little overlay is a model of the head of this probe, which we are basically we're figuring out where that probe is in its three-dimensional space. So it's 6 degrees of freedom. And then we are able, once we know where it is, we can actually project the ultrasound images on top. So the clinician who's doing this procedure can see the X-ray images and the ultrasound images simultaneously, which is very helpful because in the X-ray pictures, they can see the valve. Here, actually, here's the valve. They can see the valve that they're about to put in. And in the ultrasound picture, they can see the aorta and the aortic valve, which they otherwise can't see in the X-ray pictures. And this is just another example. And again, this whole technology was commercialized. We did this in partnership with Philips. And it was commercialized, and it's a product that Philips sell called the Echo Navigator that was released in 2012. Then more recently, I've been working with Siemens, and this time we decided to not only work on image-guided treatments where we were fusing images with X-ray images in the cath lab, but we decided actually to do a lot of work on actually treatment selection and planning. So prior to the procedures taking place, let's plan these procedures. So here we were looking at patients who were coming in to have pacemakers, and we were taking MRI or CT data from these patients and analyzing it and presenting that complex information in a really simplified way to clinicians. And then they could use all this information. So we got information about the movement of the heart. We got information about whether the heart's got scar, got information about where all the blood vessels are in the heart and so forth. We've extracted that information out and put it into a really digestible form for the clinicians. And then they can use that to plan what they're going to do to this patient. So is this patient good to have this pacemaker? And if the patient is good, yeah, let's take that information, put it into the operating room, the cath lab, and then use that to put the pacemaker in. So this is something we built recently, and it's actually undergoing testing at, we've done the testing at St. Thomas's first, and now we've deployed it in 4 or 5 other hospitals around the world, and they're testing it out on a larger group of patients. Because often when you make something, you know how you made it, you know how it works, and it's good for you, but you have to make sure that it works with other people using it as well. A really important thing. Just another example of some work that I'm doing right now. So these are some X-ray images acquired from a cath lab, in fact, during a pacemaker implant. And what you do with X-ray pictures is you want to, because they involve ionizing radiation, you want to acquire them at really low X-ray dose. So what you see here is the typical X-ray picture from the cath lab. It's very grainy. This like grainy appearance is to do with the fact that dose is quite low and there's a lot of noise in this. And what we did, we developed a CNN. convolutional neural network to actually learn how to change a really noisy image like this into a very clean image like this. So this image on the right is just derived from the image on the left, but put through the CNN, which denoises the image and makes it look like as if it was acquired with much higher radiation. So what's the use of this? What we can do is we can take even worse image than this, acquire an even lower dose, and then turn it into an image that looks like this. This image is acceptable. So the idea is to be able to turn the radiation down, and then that will obviously pose less risk to the patients who are undergoing these procedures and the staff who will get also exposed to radiation. Keep on going. So then I went into looking at robots, got interested in robots. And my real interest in robots is like making robots do things by themselves. So because I've worked for a long time in catheter procedures, we decided to make some robotic catheters. So this is like a catheter, which normally you'd be putting inside the patient. So we made a catheter that actually could work inside an MR scanner. So here's the driving mechatronics system. And we actually managed to get enough intelligence embedded into it that if we had a 3D model, like a scan, then we could get this catheter to self-navigate inside the model. So this was basically, we had like a model of a heart, and here we printed it out so we could actually see the results. We could test that theory. You could see it navigating inside the heart. So that was an interesting project and still ongoing, actually. And then we decided we're going to make some robots for doing ultrasound scanning, because ultrasound scanning is difficult, and getting robots to do it might make some sense, because robots make difficult things easier. And so here we tried to tackle the problem of fetal scanning, so scanning women that are pregnant to make sure the baby's healthy. And we built this robot which has two arms. Obviously, a human being that scans only does it with one arm, but this robot can do it with two. And also it's quite intelligent in that it can be coupled to a AI system which automatically looks at the images and actually helps the robot to move and analyze the images to make sure that the data acquired is good, and that it also look at the images for any abnormalities in the fetus. And that's ongoing, and currently we're testing this in some healthy volunteers, so not pregnant women yet, but hopefully moving on to that. We've already scanned about 100 people with this robot. We also make robots for intra-body ultrasound probes as well. So this is an example of an ultrasound probe that goes inside the body. In fact, this is what you saw in the X-ray picture earlier. And again, we made a robotic system for this and actually made it really intelligent. So you can put it in and it will self-steer and get all the different views. It's used for cardiac imaging. Keep on going. 3D printing, making bone implants. So any of you that did my module, the medical physics module last year, you might have been exposed to this because my student Antonio Pontichi has developed a way of helping our thoracic surgeons replace bones that have been destroyed by cancer. So what we do for these patients is we scan them with CT. We segment out the bones that are coming out. We then print these bones in cheap plastic PLA. We create a negative using silicone. We sterilize that negative, give it to the surgeon. The surgeon then in theaters pours in implantable bone cement into the mold, creates the bones, and then stitches them into the patient. So this is like a very lovely use of 3D printing to impact patients, already impacting patients. We also make really nice models of different parts of the human body. So these are models of the chest, again, to help doctors to practice keyhole surgery. So this is the skin, the ribs, the lungs, the heart, and we use these to train people for endoscopic surgery. Already being tested with clinicians in one session of training and being improved currently. And then here we trying to make some new printers that can print stuff that is very hard to print. And one of those very hard to print materials is silicone. So silicone is really good material, biologically it's biologically compatible, but printing it is not that straightforward. And so one of my students here, Wang, she made this printer that basically prints silicone. So far she's made some nice things with it, like for facial prostheses, ears, nose. These are one of the key things that you might want to do with such a printer. And also some valves. So this aortic valve, which you actually put into a flow circuit and tested with a pump to see if it actually is functional. And yes, it was functional. Before, she was making such valves via a very long and laborious technique, and now she can just simply 3D print them. She also prints complete heart models in soft materials, which are used for testing new devices, catheters, and other devices that we're making as well. Okay, so there's a lot of content in that slideshow, and I could spend like 2 hours going through it in detail, but I've already exceeded my time. So in summary, this healthcare technology is a good one to get into. It's very impactful, and the careers are booming, and they're going to carry on booming. And it's a great way to take your knowledge that you have and deploy it to something meaningful. And if you are studying undergraduate physics, it's a great way of using all of that that stuff that you've learned. And you have a lot of choice in where you can work, and there's really opportunities in all of those 3 areas that I mentioned. So industry, healthcare services, and at research universities. And often these three things they work together often for most projects. Whether if you're in any one of these, you're definitely going to get exposure to the other 2 for sure. Okay, that's my talk. So thanks for listening. And I'm happy to answer any questions.
Awesome, thank you very much. Let's see if we can get some questions in the Q&A. And otherwise, I have a question.
Yeah, sure.
About the difficulties of 3D printing silicone. Like, how is that? Like, what problems do you face that you wouldn't if you're using other materials?
Well, so most other 3D printing is you use heat, and normally heat melts something and turns it to liquid, then it goes back to solid. Or you use light maybe to cure something that's liquid that's photosensitive. Silicone's unusual in that it basically there's many different forms of silicone, but typically you use a 2-part silicone that when you mix it, then it cross bridges and links, and then it starts to set, and that can be accelerated by, for example, by heat or by UV light or something like this. Yeah, you can accelerate the curing process. The problem with printing silicone is it's very viscous, and it's very viscous, so it's very difficult to pump. And on the other hand, it's not that viscous that it will when you extrude it, it will sort of if I bring back my slides to that movie, when you extrude it, that it will sit without flowing. Yeah. So these are the challenges. You have to be able to get the viscosity right so that it can be extruded and it will stay put, basically. And if it's too viscous, it becomes very hard to pump it through the nozzle. And if it's not viscous enough, it'll just make a blob. It'll make a mess. You're never going to get something beautiful like this nose or this ear, or even lovelier, this valve.
All right, thank you. Let's see if we have any questions coming in.
So there's a Q&A section on the bottom of your Zoom screen. If anyone wants to, if you click on that, you can submit any questions that you have. And I think you can also use the chat. Yes, I have another question. So you mentioned how the silicone viscosity is the problem with it. So what was changed with the printing to make it so that the silicone was the right viscosity?
So what Xu, so Xu Wang is well, you probably know Xu from last year actually. What Xu did was she added fumed silica, which is actually something that you find added to a lot of household products as a thickening agent. And so she took fumed silica, added it to the silicone, and then carefully measured its viscosity until and then tried to print it. And then she just, did that for a series of mixtures of fumed silica and silicone until she managed to get a mixture that printed well and could be pumped. The thing is, right now, we got some issues in that the viscosity is so much that the pump that we had designed wasn't robust enough, so the pump just disintegrated. But we are now redesigning that pump with better materials so it can withstand the amount of force that's been applied because of having to pump this highly viscous liquid. So we got some questions. What are some ways to get experience before applying for STP? Is experience required for the NHS STP? So the NHS STP scheme, and so we're very fortunate in that we're one of the biggest providers in the UK for that. And so if you need to know more about that scheme, you can get in touch with my colleagues who run the scheme. So Dr. Adam Shortland, Dr. Lefteris Leviatros, and Dr. Enrico De Vita. And we've had a number of students who've actually graduated from our undergraduate program and gone on to join the STP scheme. So if you want to know from the course directors about it, and if you want to know from the students, just let me know and I can put you in touch, what the requirements are and so forth. Do you need some experience? I think you just need a relevant undergraduate degree, and if you're doing physics, your physics degree is going to be highly relevant. But it is very competitive, so you need to really it would be good to have maybe some healthcare related project or some relevant experience to set you aside from all the other applicants. But yeah, they really look for the top people, and the beauty of that scheme is that it's basically a job that pays you to study and get qualified. So you're working in the NHS as a trainee clinical scientist, doing our MSc in clinical sciences part-time over a number of years, and 3 years, and earning money. So it's really good, but super competitive. So if you want to go for it, you need to plan a bit early. You can find out more information on that scheme from the if you just Google that STP scheme, and it'll take you to the training website, which will give you all the details for that. And I strongly recommend, if you're considering it seriously, that you get in touch with my colleagues, such as Adam Shortland or Lefteris, to get a bit more information on, and also talk to some of our students who went from undergrad to being on the scheme. So especially now that hospitals are closed off, so the chances of shadowing work experience. Okay, so same follow-on question. Yeah, but the shadow, I don't think the shadowing is that important. I think having some relevant experience, so you could maybe get involved in some project that was related to the subject area of clinical sciences, and that's really, you guys are at a real advantage because you've got us here who are helping to deliver that program, and you've got the biomedical engineering group that will be able to help you to get that experience. So if you want to just if you want to go for that scheme and you think you want to up your CV a bit for that prior to application, then yeah, do let me know, because I will assist you in trying to get what you need. Will you be running undergraduate summer research project next year? Yes, we are running some undergraduate research projects in 2021. So we've got a number of projects that are available via KCL Engineering Society. So if you know the folk in KCL ES, get in touch with them. And I'm happy to open up those projects to students outside of my school. I mean, that's always the aim. It would be nice to have students who are from other programs to access our summer research projects. So at the moment, those projects are not funded. They're done in kind. But the other thing is to get in touch with one of our academics in my school and maybe trying to ask them if they can put a curve project together if you want to do a funded summer placement, the King's Undergraduate Research Fellowship. Okay, what else have we got? This might not be fully relevant, but I've heard of stuff like that where you're working in research, so you're getting work experience and get a PhD from it. Yes, so there are opportunities. So if you were a clinical scientist, so you qualified, you did the StP, you became a clinical scientist, and then decide to do a PhD. The NHS can help to fund your PhD, so you could do it part-time while working, and also get funding to get you that PhD. And again, people like my colleagues, those names I just mentioned, they all have done PhDs, so they're clinical scientists with PhDs. So they could really advise you. So the answer is absolutely, you could, for sure, you could do that. Yeah. Do you think the way robotics in healthcare is taught and approach will be subject to change to include the addition of knowledge on the Internet of Things, 5G? Yeah, we already so it's not for us. It's not an undergraduate. So we don't in biomedical engineering. We're not teaching IoT or like communications at the moment. It's not part of our syllabus, but certainly in the research domain, yeah, for sure. I mean, the robots that I showed you, like that intrabody ultrasound robot that I showed you, we already made that wireless and put in the IoT technology into that, so that all the different components are have some sort of autonomy and then work together. So absolutely, this is actually a big area. This IoT thing is a big area in healthcare tech at the moment. We recently just put some big grant applications in around this. So absolutely, it's and 5G is huge, because 5G. The thing is, like, if you want to do stuff wirelessly, like wireless robotics or wireless or remote or wireless, like imaging, for example. Before, like, you didn't maybe have the bandwidth and the robustness of the communication. Now with 5G, that's like gonna step up. So people can do like remote ultrasound or other types of data streaming that actually really need a robust transmission. So that's absolutely, that's a big area. So if that's something that you're interested in, that's an area to get into. Do you have any projects that you're particularly excited to work on? I'm actually excited to work on everything I showed you today. I'm excited to work on all of this stuff and always thinking of new stuff. So this like 3D printing stuff that I've been showing you is like super exciting. For me, it's like a fascinating area, because it's so rapidly moving, and it's like the silicone printing. It's like really new. There's only like about 2 companies that offer commercial silicone printing solutions right now, and they're super expensive. So we come with a solution that literally cost a few £100, which is like, the things you could do with it, because you can make soft robotic actuators. You can make implants, because silicone goes into the body. So like these valves I'm showing you, well, who knows? They could end up inside at some stage. Do you have any projects? We'd answer that one. How do you enjoy the cakes you made with a 3D printer. Yeah. So we actually making a lot of different things with 3D printers. So printing icing and chocolate and printing pancakes and all sorts of stuff. So that's the fun side of 3D printing. Good. We've exhausted the questions suddenly.
All right, great. Unless anyone has any other questions, I think we will start to wrap up then.
Oh, I have one question. Sorry. I'm just like, could you explain what the entire Internet of Things and 5G thing is in healthcare? Like, what would that include?
So I can, just use the example I just told you. So basically, like remote robotics is a great example. So, or say if I go back to my, I don't know if am I still sharing screen?
Yeah.
Yeah. So like this robot here, which is an intra-body ultrasound robot, we convert this to IoT and 5G. So we did that already, and so that means I could be sitting here in my house in South London. And this robot currently is in Beijing at the moment. I could control this robot from here, no problem. Yeah. So it's about, and I could receive the images that it was acquiring back as well in a reliable way. And then just like having a complex system and then dividing it up and making each part have some embedded control and then wirelessly communicate with other parts. I mean, there's so many good examples. It's like, for example, the artificial pancreas, which has a glucose monitor connected to an insulin pump. I mean, this is an example of systems that are wirelessly enabled and communicate to work together to accomplish some common task. Could I write down the names of my colleagues? Yeah, sure. I'll tell you, and you can guess their emails because they're all KCL. Adam Shortland, Lefteris, Levy. I think it's. I got to check the spelling of Lefteris's name. I'll just check the spelling of Lefteris's name. Hold on. I will just stop sharing for a sec. Let me check Lefteris's spelling. Livy, yeah, hold on, Livy. Yep, that's correct. And Enrico De Vita. Check that as well. Enrico De Vita, correct. Okay, there you go. Did that come into the chat?
I can't see it. Perhaps you can answer it under the Q&A. Oh wait, maybe. No, I think it's under answered. Yeah, it's under answered questions.
Is it there?
Yeah, it's there.
All right. Okay. Oh yeah, it's there. Okay, good. Nice.
Awesome. Do we have any more questions? I don't think so. Okay, well, thank you so much for opening our lecture series. It was really nice to have you. Next session will be on December 14th, and then we will have Dr. Leah Lee, so check back in for that. Yeah, have a nice evening, everyone, and thanks again, Kawal, for coming.
You're welcome. Take care, guys. Bye.
Bye.